In this series of videos, with the initial COM stands for Computer Organization and Microprocessors, what we're going to do is we'll focus completely on how are the computers designed from grounds up. In previous programs, we've talked about logic and how logic can be put together to build a basic processor. In this case, what we're going to say, now that we have a basic processor, how we can use this to build a full system that automates things, or an actual computer, and think that is the way we understand it. In order to start there, most of you by now have learned a high-level language. So let's go ahead and start at the very beginning of talking about computers, talking about what happens when you give instruction to the computers in the form of a program. What ends up happening to it. So let's go ahead and start with that. Let's go ahead and take a quick gander at what happens there. So you may be writing a high-level language, and the reason it's called high-level language is because it is abstracted, is simplified for human use more than anything else. And so you potentially, if you're writing in a language, let's say like C in here, or it could be Java, it really doesn't matter. Then you, let's say you write a simple function, which is, this is a swap. We'll take an array and swap elements back and forth. And so what happens? Does the computer understand this and is going to execute it? Computer, in a broad sense, yes, it would understand it, but in reality, what's going to happen is that this high-level language will be fed into another program whose job it is to take this and turn it into instruction that the underlying hardware understands. That's called an assembly language. An assembly language, the difference between assembly and C is designed for humans. So there is no one-to-one correspondence between each statement you write and some hardware that is going to execute that. The compiler, what it does, it takes your high-level language, breaks it down to its individual executable code, which we call assembly instruction. For example, add WF from one location to another location, and then put the result in one of those two locations, is an example of an assembly language. Pick micro, which I've used as an example here, is a language, is an assembly language and an architecture which is used by a company called Microchip. It's one of the largest microcontroller manufacturers or designers in the world. And so what happens, that's, we're not done yet. All this means is that now every command I have is actually has a correspondence in hardware. What I need to happen is every one of these instructions have to be translated to a binary number, and as we know, binary numbers are basically zeros and one. Now we're getting to what we call a machine language. Once we are here, this machine language, of course, can be understood but by basically open or closed transistors, energy or no energy, with zeros and ones. And now we can turn into the underlying hardware, which is electrically or driven by electrons, to actually manipulate this. And at that point, if we have other machine languages, that binaries or other things we want to include, we included with our piece, and then now we got an executable code. So if you want to think about what happens, is that we have a human readable, easy to understand stuff that humans write, and then we compile that. Humans also do assembly language when they have to, but most of the time, if you can get away with a simpler life, you're going to get away with a simpler one, which is the high-level language. And as a matter of fact, as the time goes by, these languages getting higher and higher level to make it easier and easier to write stuff. Java, for example, is an example of a higher level language than C because it's much easier to work with. Assembly language is much closer to the hardware, so you're manipulating the hardware activities at the same time, but it's harder for humans to understand and deal with. And then, of course, at the end, it would be almost a nightmare, impossible to design any system of any complexity if you have to write your code in binary. But the good thing is we have programs such as compilers and assemblers and eventually linkers that can do that. So this is a four-step process from C before it actually we have an executable code that runs. Okay, so let's go back and start having another conversation about what are the big items that make a computer or an automated system. So we'll go ahead and start with the inner core. Inner core, or the underlying everything, is the hardware. Okay, so we've got hardware sitting at the core of everything. What's hardware? Well, hardware, potentially you have to have a piece of hardware, a bunch of transistors. We usually call these, usually we name them CPUs. We have to have the CPU, which stands for Central Processing Unit. There might be other devices in there, but the job of this is, as it sees those binary zeros and one, it decides what it is that it needs to do. Does it need to add? Does it need to subtract? Does it need to loop? What does it need to do? That's the job of the CPU. Now, in addition to the CPU, you have to have a place where you can remember stuff and all that. That's a memory. CPUs and memories, we're going to come back and talk about them later on in a little more detail. Some other things you need to have a way to get input, and you have a way to have to share whatever the result is with the outside world, so you can have an output. So let's think about what the inputs could be. Inputs could be something like a keyboard, like a mouse. It could be an internet, or not necessarily internet, but some sort of a network incoming data. It could be any kinds of device. Could be a joystick. It could, and for example, if you're designing a computer for a car, for fuel injection, the input may be the output of the sensor, which says whether we have a too rich of fuel or not too lean of a fuel, so it can change the mixture of fuel and air to get the right mixture. So the input will vary all over the place. Outputs, again, as we mentioned, output could be the most common one we really look at is a monitor. So you could have a monitor, and monitors are made out of pixel. For example, you may have a device that is a 1280 by 1024, and all that means basically is that you've got 1280 dots across the screen and 10,024 dots down the screen. Each one of these dots can be turned on based on what is driven. They usually are organized such that you have 8-bit that tells them what an R is, 8 red color is, another 8-bit that tells them what the green is, and then another 8-bit which says what is the blue is. So for example, if in hex, if you give them, let's say you give them a hex number, which is 2, 5, and 15, let's say, or F, this basically says the blue gun, the blue portion is turned on full power, green is turned on somewhat of a power, and 2 red is turned on somewhat. So it's kind of a grayish color, because if all were full power it would be white. It's a grayish color with a blue tint to it. That's pretty much what it is. So that's the display that's most common. Well, we could be using other devices. For example, if you're building a computer for fuel injection, the output may be the voltage that would drive the valve that opens the air or the fuel. So that might be one output. The other one would be the networks. We could send our output over a network. For example, if you have a server farm that nobody is in it, it could be there. Networks could be of the personal type. For example, could be USB, Bluetooth, or other things like that. Those are called the personal network. They could be local area networks such as Wi-Fi that we use for communicating amongst computers, or there could be WAN. It could be a wide area network, which are stuff that goes beyond the building and crosses maybe multiple cities or cities as a whole. So those are the type of ways we can do I/O out of this. So that's the hardware piece. So in addition to the hardware, what else is there? Well, hardware by itself is not going to know what to do. You need to have a set of code around the hardware to make it work. And these are in PC sometimes, but all computers, this is referred to as operating system. And in PC, I'm going to operating system, or for brief is referred to as OS. I will include BIOS and basic I/O things as part of that. In Linux, that might be part of a kernel, but that's called an operating system. So I've already kind of mentioned a couple examples. For example, Windows is an operating system, and then Linux is another operating system, and there are many more, but those are, and Macs, of course, Apple iOS is another one. But those are the biggies. There's a ton of other operating system depending on what folks are trying to accomplish. The job of an operating system is to make sure there is enough software to bring the hardware to a point where someone could actually write an application without having to worry about when the application gets started and how to reach the keyboard, how IOs, and how to do networking and all that, and then if I have two applications who wants to run, who's going to run first, who's going to run second, that's all taken care of in the operating system. Let's take a look at, I have this computer I have is a PC that is running this presentation software on it. So let's take a look. For example, if you do a Control-Alt-Delete on your computer, you will get a interactive development environment, which is what we're going to use to program our microprocessors. Some of the other applications here, I have a MATLAB running, that's an application. I probably have Word. Camtasia is the tool I'm using to record this presentation. I have some other applications in here. ActiveHDL, which you're familiar with, hopefully. That's the if you've got a FPGA or some other thing you want to program or build your hardware by describing your hardware. Scilab, which is a MATLAB lookalike. Skype. These are kind of applications which sit on top of the whole thing. So let's go ahead and go back to the notes somewhere in here. So that's pretty much the computer. So we got three layers. We've got the hardware stuff that sits underneath, and we briefly talked about what they could be. Operating system, which is all the housekeeping and making sure they can handle the basic I/O, start application, allocate storage, memory, and process to different applications. And then, of course, at the end is an application. So when you buy your computers, your typical computer, you will get everything inside this red box, but you don't get the applications. Your applications, well, sometimes you get some free ones, but most of the time you have to acquire that depending on what you want to do. That brings us to the end of the introduction phase. When we come back on the next one, we're going to talk about CPU and memory types and move on from there.